And then we can move on chapter 5. I will just do an introduction today on temperature and gases, you know. I feel like it's important that we go over that since Tuesday we have the quiz on chapter 4, which again is not complicated. There will be a couple of problems here and there, but it's mostly going to be conceptual, right? There is a few concepts in there: pressure, density, the Pascal principle, all right? Not necessarily a problem, but to understand what's the concept, right? Applications that we did at the end, okay? So I think that weekend should be enough, but I'm thinking maybe on Monday or during the weekend, just be on, or you can send me an email. I will see if I can give some office hours, all right? It all depends on time, right? So if I have some time, I will do office hours, okay? But a good exercise that I think will help, let me see here what's going on. Will be to do an exercise on pressure, all right? So let me just send a message here as a student. Okay. Let's take a look. So this is similar to the one that I gave you in the guide. So they give you something like this. A container with oil on top and water at the bottom, right? I mean, you probably are used to that. You know that oil has a lower density. So the oil is here and the water is at the bottom, and it has a thickness of 3 meters. That's a lot actually. So anyway, and then you don't know, but they give you here X for the thickness of oil, and they ask you what's the value of X if the gauge pressure at the bottom. So the pressure here is equal to 5, okay, something about the gauge pressure, pascals. Remember that the example of the pressure of the tire. The pressure of the tire is the gauge pressure. The absolute pressure will be if you add the atmospheric pressure. So in PSI, normally it should be around 35, right? But if you add the 14.7, you will get 49, almost 50 PSI for the pressure inside. That if you consider the atmospheric pressure. But since the atmospheric pressure is everywhere, right? Of course, it depends on the height. The higher you go, the lower the pressure, right? So then we talk about gauge pressure, gauge pressure. So that's the one there, okay? That's because it's open. So if I wanted to get the absolute pressure, I would have to add the atmospheric pressure in Pascal is, you remember, the atmospheric pressure in Pascal was 1.01 times 10 to the 5 pascals, right? So the densities are also given. The density of oil, the density of water, so this, which we can do as density of water, as it says in the book, is 1,000 kilogram per meter cube. And the density of oil, so rho of oil, this is rho water, which is D of O, as in the book, is 510 kilograms per meter cube. Okay? So how do I get the X if I have the pressure here? Well, you know that even though it's open, so the atmospheric pressure affects both. So if we disregard this and we measure the gauge pressure here, that will be the gauge pressure there of oil, which is equal to something. There is some pressure here as you go deeper and deeper. We can say that in this section in water, so it's right here, in water, the gauge pressure at the bottom due to water minus the gauge pressure due to oil is equal to the equation for pressure that varies with height, the density of the fluid, which will be water, times gravity times height, which is 3 meters. And we have the density of water, it's 1,000, right? So this number we know. We know this. This is this. So what's the gauge pressure due to oil? That will be the density of oil times gravity times X. That's where your X comes from. So I think this is a very interesting problem because now we are reviewing the equation for pressure and the gauge pressure that we talk about. Okay, so 5 times 10 to the 4, the pressure of here, minus the pressure here, which is that, we have the density of oil, gravity is 9.8, times X is equal to this. This is 1,000 times 9.8, 9,800, 29,400 pascals. So as you can see, you have an equation for X. It's a very simple equation. We write this number here, so all this becomes 5 times 10 to the 4 is 50,000 minus 29,400. That's equal to 510, 9.8 times X. Oops. Oh, by the way, I forgot. That will work, hopefully. Right? So now we just do the math, we just put in the calculator. And that will help you for that last problem in the worksheet that you have there in the Canvas. So I subtract, I divide by 510, I divide by 9.8, and I get 4.12 meters. And makes sense, right? There is more oil, obviously, so I get X equals to 4.12 meters. All right, so that's basically what you have to do. It's a very interesting problem because it uses all those concepts of pressure that I don't think we review enough last class. And then there is some problems that they are very simple. For example, what's the buoyant force due to a solid gold crown totally immersed or submerged in water, and they give you the density of gold and that one of water. Okay, so that one actually, you don't need that, right? Oh yeah, so that's a good problem though. So this is basically the Archimedes principle, all right, or the Archimedes anecdote. They gave him a crown, he knew the mass, but he needed to figure it out if it was made of pure gold, and he discovered that the weight of the water displaced was equal to the buoyant force, right? Or the volume displaced. The weight of the volume displaced by the water was, and by knowing that, we know that the crown was actually made of gold. Now, they give you the mass of the crown and the density of the gold, and they give you the density of water. So how do you calculate? So that's a good problem. Let's do it here, and with that, we conclude with chapter 24, chapter 4. So they give you a crown with made of gold with mass 0.60 kilograms, and they tell you that the density of gold is equal to 19.3 times 10 to the 3 kilogram per meter cube, and the density of water find the buoyancy. I could give you a problem like this actually. Easy. It's application of formula. The buoyancy is equal to the density of the fluid times gravity times the volume of the object in water, so submerged. Now, the crown is totally immersed, as it makes sense, right? So, easy. The density of the liquid is this. This is the density of water times gravity times the volume submerged, 1,000, 9.8. Now, what's the volume submerged? Is the volume of the crown. Now, I have the mass and I have the density of the crown, right? The mass of gold, the density of gold. So, you can say and do this. The volume of the crown will be the mass of the crown divided by the density. Because from the density equation, you can use that. So then here, you will put parentheses, 0.60, the mass, divided by the density, 19.3. 0.6 and 9.8 divided by 19.3. 0.3. So the buoyancy will be 0.30 newtons. Okay. We did a problem with the Archimedes principle as well last class, where the weight had to be equal to the buoyancy, right? Remember that if you're given the density of the object, you can find the mass by multiplying density times volume, like you see there, right? In this equation there, the mass equals to density times the volume. And the weight is density times volume times gravity. Now, just remember that when you want to get the weight of the object, you need the density of the object. When you want to calculate the buoyancy, for the buoyancy, you need the density of the fluid. So, for example, if I gave you oil, the buoyancy will be less. So, most likely, an object will tend to be immersed more easily in oil than in water. Okay. All right, guys. So that's basically chapter 4. It's a good idea to start with that. Just a review of a few applications. It's here in the. Let's share this now. It's there. Only 8 problems only, not many. All right. Plus what you have in WebAssign, right? Okay, so let's open this. Chapter 5 is another interesting chapter because who is here today, by the way? I have to see the attendance. Okay, we're missing 2 people. Okay. What happened there? Oh. Okay. So, temperature and heat. We have discussed fluids, right? We first introduced the state of matter. We talked about solids, gases, and liquids. We talked about plasma, and I did mention that there are other exotic states of matter. But at the end of the day, in chapter 4, we discuss more about fluids like water, oil, right? Even though we did bring into account air as a fluid, right? When we discuss helium balloons. But at the end of the day, all those concepts about buoyancy, and later on in physics, we discuss viscosity and surface tension. All those concepts are more related to fluids. So we really haven't discussed much about gases, right? The gaseous state. So that's the idea with this chapter, is to bring into account temperature, the behavior of gases, the laws of thermodynamics, as you see there, specific heat capacity. So in that case, we will go back to liquids, but then we'll do phase transitions, and then engines and the second law. So this, it looks like a long chapter, but I want to focus on certain key points. Like for example, we're first going to talk about temperature and thermal expansion and gases. And then we can talk about a little bit of the first law of thermodynamics and leave it there. And then at the end of next class, we can start talking about specific heat capacity and heat transfer. So then we can finish with phase transitions and talk a little bit about thermal machines. all right? So the period for this class should be until, actually, I think this class, this chapter, will be up until the election day. Which, by the way, I should ask, are you guys gonna be in class that day or not? It's November the 3rd, that's a Tuesday. Are you guys gonna be in class? Do you have anything that prevents you from being in class that day? Nothing? Okay, that's good. So I don't really wanna give it off, all right? Okay. So why do we study heat and gases? Because that's how we can understand storms, cyclones, hurricanes, right? So when you look at hurricane from the space, it looks like a whirl, right? Like a twister, a very big twist. It's not really a twister, right? It's a whirl, very strong wind with an eye in the center, right? Now, those strong hurricanes, they have winds that can have a very high speed, right? And they can cause a lot of distraction because normally they can flood a city or part of a country, like for example what happened in the Bahamas or Katrina or in New Orleans in 2004, right? And also killing a lot of people. So we have to understand the idea of phase transitions, condensation, and evaporation of the air, right, or water, right, in the ocean, and how this can produce a chain of events that can produce a very active hurricane season. So the way they develop is because the ocean is very warm, especially in the Caribbean, right, around Bahamas, Mexico, Florida. So that warm ocean water evaporates, and then it's, because it evaporates, it's hotter than the environment. It goes into the air. It's carried high towards the clouds. So now then, the cycle of water condenses. And then what happens here, for example, guys, in New Jersey, is that we have a lot of thunderstorms. When it's hot for like 3-4 days after a heat wave, for example, I remember one in July this year, because I spent a whole weekend on the shore, right? But it was very hot. And after that, we had a very strong thunderstorm. That's because of the condensation. You saw all the heat that is heating towards the ocean water and the lakes in New Jersey, but mostly the ocean water, they go up. So when this water condenses, then it drops. And then by dropping, it releases energy, right? This energy rushes and then it is replaced by the rising air. And then you can have an encounter of different air temperatures. And then you can start having high winds. In fact, we don't have hurricanes in New Jersey, right? But we do have thunderstorms. And normally they come with strong winds. That's because of the whole idea of evaporation, condensation, which are the key of the cycle of water. So the idea of this chapter is to understand that, talking about the physical processes, the physical changes. We call that phase transitions, or phase change. When you have a solid melting and then becoming water, and water evaporating and then condensating. All right? So in order to study this first, we have to understand the idea of temperature. So I always tell people, right, the misconception with temperature is that it tells you if a liquid or a gas or something has more heat. And even though they are related, they don't mean the same thing, though. Temperature, physically speaking, is a measurement of motion. So we already have spoken about solids, liquids, and gases made out of atoms. And these atoms are moving at random speeds and they collide with each other. So even though we can measure or we can define temperature as the measure of how hot and how cold something is, we first of all need a scale. But we also need to understand what temperature is. So as particles, right, as atoms or particles inside the atom, right, we're talking about subatomic particles, are moving faster and faster. They have more kinetic energy. That is what rises the temperature in a thermometer, as you see in there. So the scientific definition of temperature is the average kinetic energy of particles. That's basically what it is. The more energy, the more speed, the more temperature. In fact, we're not going to see it now, but there is a whole section that studies the kinetic theory of gases. And that's where we can get something that we call the root mean square velocity of a gas, of particles in a gas. So there are ways, because we can get the energy of the gas. And if kinetic energy is equal to the energy of the gas, then we can get a whole bunch of stuff. But anyway, don't worry about that. Just remember that temperature is a measurement of the average kinetic energy of particles. And that's why the absolute zero is defined as a temperature where all atomic motion stops. Okay? Which we know doesn't really happen. So it's sort of like a endpoint of temperature. Okay? So how do we measure temperature with a thermometer? So what's a thermometer? It's a device that allows you to measure the temperature of a substance by using different concepts. In some cases, it can give you the change of temperature, right, based on a column of mercury, as you can see there. All thermometers used to be based on columns of mercury. That's the liquid in crystal thermometer. So if the temperature was up, the length of the column will go upwards. And the other way around, if it was colder, the temperature will, the length of the column of mercury will go down. But what is the scale that we use? In the US, we use the Fahrenheit scale. So I can say in a normal day of summer is 90. In a normal day of winter is 20, 25, probably 30s. In a normal day of autumn and spring, it can be 50, 60s, like today. So what is the problem with that scale? There are a couple of problems. Even though it's commonly used here in the US, the main problem is that it's a scale that is not used worldwide, right? If you go just to Canada and you look at your phone, the weather app, you will see that automatically it will change to Celsius, and the temperature and the road signals will go to kilometers. So just here, I'm talking about what? By plane 1 hour away, right, to Toronto, or 1 hour and a half, things have changed because of the system they use. So what's the universal system to measure temperature? Celsius. And what's the scientific system? The Kelvin, as you see there, what you have in front of you. So I gave you 2 thermometers in there. 2 and 3 scales. So you have the normal temperature that you use from 212 boiling point to 32 Fahrenheit, which is the freezing point, and below. But right next to it, you have the Celsius, the one in the middle. You want to know why Celsius is a better scale, or is a more common scale that we use? Oh wait, am I? Okay. The reason is because, guys, just like centimeters and meters is defined by powers of 10, but more than powers of 10, it has 100 divisions within the first 100 degrees, and they help you to locate the boiling point and the freezing point. In fact, we calibrate thermometers by using those. We use the freezing point of water and the boiling point of water to calibrate a liquid in crystal thermometer, for example. And once we calibrate it, we can have a scale, which is the Celsius scale. Goes from 0 to 100, but you can have also negatives. That's below the freezing point. And in the case of the Fahrenheit, it goes from 32, that's the melting point, or the freezing point of water, and that's below that, it starts becoming into the negatives. Now, you can see that most of the temperatures don't coincide, but there are two values that do, -40 and -40. That's because of how the scale changes. There is a linear relationship between Celsius and Fahrenheit, by the way. Okay? The scale in Fahrenheit and the scale of Celsius, they do have a linear relationship, but they don't coincide in their freezing and melting and boiling points. Anyway, let's go to Kelvin. Why do we define the Kelvin? Because that's how we define the absolute zero. The absolute zero is defined as 0 Kelvin. And when you extrapolate in Celsius, the absolute zero is around -273 Celsius. How do I know that? By the equation that you have there at the bottom, here. This equation, right? When the temperature at Kelvin is 0, the temperature at degrees is -273.15 Celsius. So that is the absolute zero. Okay? And as you can see there, you have the three scales, and you can nicely see how the Celsius scale is going as tens, right? Which is one of the reasons why we use it instead of Fahrenheit and Celsius and Kelvin. Now, Kelvin is used a lot in thermodynamics, for example, or gases. So don't make no mistake. We will be using Kelvins at some point. Now, they give you a few tables for a few values here, for the absolute zero, for the oxygen boiling point, for the normal body temperature. I think you guys should know by now, right? 37 degrees Celsius or 98.6 Fahrenheit. If you go beyond that, let's say 100 Fahrenheit, then obviously that's when things become like, that's when they start red flagging you because of this pandemic. Anyway, so as I explained before, temperature and energy are closely related. All right. Now, with the Kelvin temperature, as I mentioned, the Kelvin temperature of matter is proportional to the okay. So that's basically what I said, right? Not just the Kelvin, the temperature itself. The temperature of matter is proportional to the average kinetic energy of the particles of a gas, of a liquid, or a gas. That's this picture there. So at 0 Kelvin, which is a limit for this, you see no motion of the particles. At 200 Kelvins, you can see that particles are moving somehow, maybe not very fast, but they're moving. They are still below the freezing point of water. And then when you go above the boiling point, the melting slash freezing point of water, you have particles moving at at higher speeds. Okay? All right, guys. How will you answer that question? I just said the answer, by the way. The average kinetic energy of the atoms in a gold ring determines what? The average kinetic energy of the atoms in a gold ring determines what? Determines its temperature. All right, don't forget. Choose the incorrect statement. Absolute zero is what?
The second one?
Yeah, 0 degrees on Celsius scale. It's not. In the Celsius scale, the absolute zero is around minus 273 Celsius, okay? If the temperature of something has raised by 50 degrees, that means, okay, you can look at a table, but you can also do this. The equation that relates Celsius and Fahrenheit. And what is it? Celsius over 5 is equal to Fahrenheit minus 32 over 9. Okay? So, let's see. Let's take a look at what do we get when you raise something by 50 degrees. All right? 50 degrees Celsius divided by 5 is equal to Fahrenheit minus 32 divided by 9. 10, 90. You get 122. So not really, right? Not really. So that's the equation for going from Celsius to Fahrenheit. Okay. All right. So we know now what temperature is. We know we can measure it in 3 different scales, where Celsius or Kelvin are the ones that we use the most in science and also maybe not in daily life here in the US, but if you go, for example, back to South America or Europe, right, or even Mexico or Canada, they use Celsius for their measurements. One property about heat and that relates with the change of temperature, guys, is thermal expansion. It's a very crucial concept to understand a phenomenon in nature where objects, depending on their type, but regardless of their volume or mass, they tend to expand. So what is the idea behind thermal expansion? is the fact that when the temperature of an object changes drastically, even though it might take some time, but you have the temperature of certain object changing for quite something. We're talking about probably like what? Less than 100, but more than 70 degrees Celsius, which is a lot. So in a day of summer, we know that temperatures can get really, really high. So in some places around the world, even here in the US, when they build train rails, or when they are going to build, a pedestrian road or blocks where you can walk or even run, you will notice that there's always a gap in the tiles. That's what I mean. In the tiles that you have on the floor, in many places there are gaps in between. So why are there those gaps in there? Is it because aesthetic, or is it because of something else? And the answer is very simple. It is there because of thermal expansion, especially with our rail trains, because an object can be a conductor, an insulator, or a semiconductor, but also an object can have a higher constant of expansion, because every object to expand, oh wait, I forgot to check. Yeah, every object, guys, solid, to expand, to have something called linear expansion, it needs to be radiated by heat, and the temperature has to have a considerable change. Or it may be that the temperature doesn't go that fast or that high, but the object has a very high coefficient of linear expansion. Now, is there surface and volume expansion? Yes, there is. There is. For example, in here, right, we have a pot, and you have normally that's a pressure reader, but you can also have a temperature reader there, and it tells you what is the temperature when you have the water boiling there. But you maybe have noticed, this is actually very interesting. It used to happen when I used to work in school last year, private school. We used to help kids with their lunch. And there was this kid who didn't know better than their kids, and the parents also, right? But this is for you guys to know. When you heat up some food, let's suppose the kid's gonna bring their lunch, and from 8 a.m. till like 11 or 12 when they have their lunch, there's some time in there, right? So normally they have it in their bag, and on top of that they can have aluminum, right? They can put aluminum on top of the lunchbox so it keeps the heat. So that's good in terms of like conservation of food. But you know what's bad? Is a thermal expansion. Because when you have something very hot for a long time, the walls and whatever is inside is going to expand, maybe not much, but just enough to make it hard to open. And that's what used to happen with a lunchbox for one of the kids. It would be very hard to open. Why? When we finally opened it, we realized that it was still sweaty. Like they put something really hot in the lunchbox, which was made of aluminum, and well, not really the outside, but the inside, not to conserve the heat. And well, it was expanding. So what we had to do, we had to lower the temperature. All right? So that can happen also with pots, right? Which is why sometimes, depending on what you have, they start jumping the lid, right? It's because it's expanding and it's going against the walls of the pot. All right? So that is interesting, right? Another example may be rice, right? When you are cooking rice, it expands because the temperature is increasing. But that's more with volume. Here we're talking about linear. All right? So linear expansion is a thing. And in railroads, they use it when they are going to build it. So, let me see if they give the equation. Oh, there it is, that's the equation. So, the equation for linear expansion, first of all, depends on this, on that alpha, which is the coefficient of linear expansion. Depends on the original length, and obviously depends on the change of temperature. Okay? So there you are, and let's take a look at an example. Okay. So they give you a 1200 meter long steel bridge. Oh, there you are. And normally, if they build it during the winter, the temperature around the winter is -5 degrees Celsius, so below zero, below the freezing point. But during the summer, it can go up to 35 degrees Celsius. Let's actually do something with this problem. I want to show you what's the meaning of 35 degrees Celsius. With this. 35 divided by 5 equals to Fahrenheit minus 32 divided by 9. This is 763 is equal to Fahrenheit minus 35. That gives me 90. So 98 Fahrenheit is 35 degrees Celsius. So very hot in the summer. So let's analyze how much will the bridge expand due to the change from winter to summer. And they have to build a bridge, taking that into consideration. If they do not, they can cause a huge accident, right? Because thermal expansion on conductors like steel, aluminum, copper is a thing. So the bridge is made of steel. And so I wanted to show you guys that's a conversion there that I did. But I want to show you guys now how to solve the problem. But we need to know, looking at the table, that the alpha of steel is 12 times 10 to the negative 6. So it's not a lot, but still, the alpha for steel or iron is 12 times 10 to the negative 6 1/Celsius. That's the unit. Okay, it's the inverse of Celsius. So on the winter, the temperature was -5 degrees Celsius. On summer, the temperature was 35 degrees Celsius. What is the change on temperature? It's not 30. The change on temperature is 35 final minus initial. minus 5, that's equal to 40 degrees Celsius. Why do I need that? Because the equation for linear expansion is the following. Delta L is equal to initial L times alpha times change on temperature. Delta L will be, okay, in the problem they tell you that the L is 1200, the alpha is that, and the temperature is 40. Oh yeah, 576 times 10 to the negative 4, which will give you 0.0576 meters. You probably think that's not a lot. Look, let's convert this to centimeters. 5 5.76, so around 5.8. Do I have a ruler here? I had a ruler here the other day. 5 centimeters is around this. Around, yeah, like that. So if you don't take that into account, right? Because not just one section, every section that they build expands. So, and this is only 1,200 meters. Imagine if it was more. And imagine that, and the change may be even more. Is we're assuming -5. -5 in Fahrenheit is 23 degrees Fahrenheit. 23, 9, wait. 32 minus 9, yeah. But you know that in winter it can get even less than that. Can get to tens. Hopefully not this winter. So that's why. Be careful with that. Now, in the slide you have also other means of how you measure the temperature. For example, they show you this. Remember that thermometers is a device that is very, not gonna say new, but back in the day they had other means. There is the Galileo thermometer, which is in the office, but I don't have access right now to it, it's closed. But we also have bimetallic. Bimetallic strips are normally what we use in ovens, all right? It's just based on thermal expansion, guys. You have two conductors there, all right? You can have steel and copper, for example, right? One will expand faster, and because of that, it will be bent, as you see there when it's hot, all right? And if it's cold, it will go the other way around, all right? That's because the two metallic strips, they are the same length, but they are from different materials, so they have a different coefficient of linear expansion. So the temperature is the same, the temperature change is the same, the length is the same, but not the coefficient that makes it change. So that's another way of measuring temperature. And then you have the thermostats, all right, circuit breakers. Normally the way they work is by using coils, all right, and you can have pointers, all right, and it can actually measure a temperature change, all right, by the motion of the spiral in within that is connected. The spiral is there, spiral I'm talking about, and it's twisted, sensitive to temperature changes. Now, let's see about this, all right? We talk about linear expansion, but they can also be volumetric and superficial expansions, all right? Let's suppose you have, for example, there, you have a hole in a block, all right? So because of the thermal expansion, every point on the solid will move away from every other point, all right? So the hole doesn't really change its dimensions, right? Because the area is expanding, all right? So the area gets bigger, not the hole necessarily, all right? Now, if the solid has a hole in it while you're doing the thermal expansion, all right, then because of the rate, because of the change, all right, it will make it bigger, all right? Because as I mentioned, right, if there's not enough change here, then the hole doesn't really change its dimension. But if you really place it at a big temperature change, then clearly the hole gets not very bad, gets slightly bigger than here. What gets bigger, what's more clear that gets bigger is the area itself, right? Of whatever this is, a piece of iron or whatever. Okay. Okay, so let's talk a little bit about gases now, guys. And then we can talk a little bit about, and then we can finish with this. We can talk about the next section, which is specific heat and thermodynamics next class, or at the end of next class when we finish the quiz. But many of you probably have heard about the ideal gas law. The ideal gas law is the fact that a gas that has particles moving in random directions has its particles colliding with each other and with the walls of the container, or the balloon in that case, and that the collisions are elastic. So there is a conservation of energy and momentum. All right. Now, what does that figure showing you? Let's suppose you have a balloon outside during winter, and then you bring it inside during, when it's hot, warmer. The first idea is that the volume and the temperature are proportional to each other. Whatever the temperature goes up by whatever factor, also the volume, as you can see there. I believe that's Charles' law. Because then we have Boyle's law. That one there. PV is constant. But if you combine Boyle's law with Charles' law, you have the equation of gases. So PV equals to nRT. We are ignoring that the particles are losing energy, by the way. All right? So, as it says there, we're ignoring the interaction between. It's not like we're ignoring. It's like we are considering those interactions to be ideal. That's why it's called ideal gas. All right? Now, what are the variables in there? The pressure, the volume, and the temperature. What is the constant? Something called the constant of gases, R, and the number of moles in the gas, which in chemistry is defined as the mass of the gas divided by the molar mass. If you have done chemistry, you probably know what I'm talking about, right? Every gas has its formula. Let's say oxygen, O2. But oxygen has an atomic mass of 32, I believe, right? Or 16. 16, yes. So then the atomic mass of oxygen, O2, will be 32. And then if you have the mass of the gas divided by that, you get the number of moles of oxygen. But don't worry about it. I'm not going to be testing you guys on that. Just remember that pressure and volume are inverse proportional. So if the pressure goes up, the volume goes down. You know what's the best way to show you that, guys? Oh, it's not here. It's later. But it's when you have a piston. Simple as that. If you have a container with a piston and you have a gas, if you push the piston down, the pressure of the gas will go up as the volume goes down because you are reducing the volume. And as the pressure goes up, right, faster than the volume, then you can have a change of temperature. That's why in thermodynamics we study different processes where the temperature can remain constant, where the pressure can remain constant, or the volume can remain constant, right? You have a system with 3 variables there: pressure, volume, and temperature. Now, pressure, we already know, pascals. Volume, meter cube. What are the units of temperature that we use here? Kelvin. There. You see the temperature there in the slide, in the figure? Kelvin. The ideal gas law is written with a temperature in Kelvin. All right? So, we use gases in many applications, not just in physics, but also in astronomy and astrophysics. Because you should know that, for example, we are here due to matter of stars, but we're also here because the whole sun was formed from what we know as a nebula, or more specific, a molecular cloud, a very enormous cloud of a gas that was between 10 to 100 Kelvin, very cold gas. And then it started to shrink and it started to come together all right? And then the center of it, due to pressure incrementing, the temperature was going up, the volume was decreasing, and then we had a protostar being formed. But before we understand that, we need to understand the behavior of certain gases like hydrogen, helium, which are the most abundant gases of the universe, and then we have oxygen, carbon dioxide, and other gases. All right? So these facts, all right, make the ideal gas law useful to describe the thermodynamic properties of different stellar objects like stars, for example, like the sun, or the origins of it. All right, these regions of gases or emission and reflection that we find in the universe. I will go over this problem later, guys. All right, next class. But remember these blimps. All right. So another way that you can have a balloon going up besides using helium is by heating up the gas. All right. If the volume of the gas is fixed and the temperature is increasing, because the temperature is increasing, right? And what's temperature? Okay, simple. The volume is kept constant, and you increase the temperature of the air inside the hot air balloon. Because the temperature is increasing, it will tend to go upwards. Hot air tends to go up, guys. Which is why, if there's a fire, you crawl. Right? Because the hot air is going up. And all the carbon dioxide is also going up with it. So you want to crawl. Anyway. When a hot air balloon gets all that hot air going up, it's pushing it upwards. But also, the pressure is going up. And if the pressure is going up, the force is going up. Because what's pressure? Force per unit area. So that is how you have a hot air balloon. All right. Besides using helium, you can use hot air, and it will go up. Of course, it has to be very hot, and you have to calibrate the balloon and also the amount of pressure so it doesn't break down. All right. A key is placed in a hot oven and warm to 100 degrees. What will happen with the key? Don't say it becomes hotter. All right. What will happen with the key? If you place a key inside an oven, it's bent, the holes become smaller, or the key becomes longer. Anybody? The key becomes longer because of the thermal expansion. The hole cannot become smaller. In any case, it will become bigger. So, there. A bimetallic strip is made of two metals that have different, okay, true or false, that's easy. A bimetallic strip is made of two metals that have different coefficients of, yes, it's true. We did that in here. All right, there it is. All right, guys, let's leave it in there. We will do problems on gases next class. But remember, we have the quiz, all right? And we have the continuation of this. Now, another thing before you guys go. When you heat the air in a hot air balloon, right? You're increasing the pressure, you're increasing the temperature. What do you think will happen with the density? maybe that's a bit more difficult. There is an equation for the density of a gas, and it's inverse proportional to the temperature. All right? So if the temperature goes up, the density goes down. All right? Don't forget that. If the temperature of a gas goes up, the density will go down. All right? All right. So we can start with thermodynamics next class. That's good. All right, guys. So I will dismiss you guys now, and I will see you guys Tuesday. Make sure you study for chapter 4 quiz, okay? Okay, stop recording now.
Thank you, Prof.